In our previous video, we learned about the Base Angles Theorem, its converse, and its corollaries, and we applied it to pretty simple, straightforward problems. In this video, we're going to apply those same concepts to more advanced problems that require you to use more than one of the theorems or corollaries or converses per problem. The theorems, converses, and corollaries that we'll be using today are the triangle sum theorem, which tells us that the sum of the interior angles of a triangle is always equal to 180 degrees. The corollary to the triangle sum theorem, which tells us that the sum of the acute angles of a right triangle add up to 90 degrees. The exterior angle theorem, which says that an exterior angle of a triangle is equal to the sum of the two non-adjacent interior angles. The base angles theorem, which says that if there are two sides of a triangle that are congruent, then it must also have two congruent angles. The base angles converse, which says that if a triangle has two congruent angles, then it must also have two congruent sides. The corollary to the base angles theorem, which says that if a triangle has three congruent sides, then it must also have three congruent angles. And the corollary to the base angles converse, which says that if a triangle has three congruent angles, then it must also have three congruent sides. So we're going to be combining all of that information together to find out the measures of each of these angles. With the problems that we're looking at today, there's going to be more than one triangle per diagram and multiple variables to solve for. For example, let's start with W. W is one of the angle measures in this equilateral triangle. And the corollary to the base angles theorem tells us that if a triangle has three congruent sides, then it must also have three congruent angles. So I could actually label all three of the angles in this equilateral triangle with a W, because they must all have the same measure. In fact, let's just focus on that equilateral triangle. If I have a triangle with three angles that are all marked as W, I can add W plus W plus W and set it equal to 180 degrees, because the triangle sum theorem tells me that the sum of the interior angles of a triangle is always equal to 180. So I get 3W equals 180, and that means that W must equal 60 degrees. In order to explain my reasoning, it requires two different reasons. We use the corollary to the base angles theorem to say that all three angles had to be W, and we use the triangle sum theorem to add those three W's up to 180 degrees. So let's update our diagram. Instead of W, let's write 60 for all three of the angles in that equilateral triangle. Okay, what about X? Could we solve for X based on what we know now? Well, yeah, we could, but it doesn't actually require any knowledge of triangles, it just requires knowledge of right angles. If I just focus on this part of my diagram, I see that that angle is labeled with a square, which means it must measure 90 degrees. And that 90-degree angle has been broken into two different angles, one of which measures 60 degrees and the other measures x degrees. So I know I could add 60 and x and set it equal to 90. And that would mean that x equals 30 degrees. And again, there's really two reasons that support why that's possible. First is the definition of right angle, that since I had an angle marked with a little square at the vertex, it must measure 90 degrees. And then I use the angle addition postulate to add those two angles together that made up the 90-degree angle. Okay, so let's update our diagram again. X would be 30 degrees. And if I look at the triangle on the right-hand side of this diagram, it's isosceles. It has two sides that are marked as congruent. And the base angles theorem tells us that if there are two sides of a triangle that are congruent, then it must also have two congruent angles. So I could put a 30 right there where you already see it, where x was before, but I could also put a 30 right here, because those are the two base angles of that isosceles triangle. So focusing now on just that isosceles triangle on the right side of our diagram, I can add the three angle measurements together and set it equal to 180 degrees. 30 plus y equals 180. Which means 60 plus y equals 180, and that would mean that y is 120 degrees. My explanations there would be the base angles theorem. That's how I applied the 30-degree angle measurement to both of the base angles, and the triangle sum theorem. That's how I added the three angle measurements together and set it equal to 180. Let's try another one. If I want to solve for x degrees first, well, x is one of the angles in this isosceles triangle, so let's start there. Since I have two sides marked as congruent in this triangle, I know I must have two angles that are congruent. Specifically, it would be the base angles. Remember that the base is the side that isn't congruent to the other two, so this side would be my base. And the base angles are the angles that are both attached to the base. So 48 is one of my base angles, and the other base angle would also have to be 48 degrees. So now I can add 48 and x and set it equal to 180. And I can solve and figure out that x equals 84 degrees. And that would be because of the Base Angles Theorem. That's what allowed me to write this 48-degree angle here, because this angle was 48 degrees, and those are the base angles of an isosceles triangle. And also the triangle sum theorem, that's what allowed me to add all three of the angle measurements together and set it equal to 180. So let's update our diagram. I've got 48 and now 84. So how am I going to solve for y? Solving for y actually doesn't require any knowledge of triangles whatsoever. If I just focus on this part of my diagram, I see that those two angles form a linear pair. They're adjacent angles whose non-common sides are opposite rays. That means I can add them together and set it equal to 180. So y must be 132 degrees because of the linear pair postulate. Okay, let's update our diagram with that information. How am I going to solve for z? Well, looking at the triangle on the right side of the diagram, it's isosceles. It has two sides that are marked as congruent. And according to the Base Angles Theorem, that means it must also have two angles that are congruent, specifically the base angles. And remember that the base is not necessarily the side that it sits on. The base is the side that's not congruent to the other two, which is this long side up here. And the base angles are the angles that are both attached to that base. So one of the base angles is z, which means the other base angle must also be z. So I can say that 132 plus z is equal to 180. So z and z gives me 2z. 2z equals 48. So z must equal 24 degrees because of the Base Angles Theorem. That's what allowed me to apply z to this angle measurement right here. And also the Triangle Sum Theorem. That's what allowed me to add all three angles up to 180 degrees. What do you think about our next example? Let's try to solve for x first. Well, if I focus my attention on the entire triangle, so forget about the stuff in the interior of that triangle and just focus on the big triangle, I know that x and 38 have to be equal to each other. X equals 38 degrees. And that's because since this is an isosceles triangle, it has two sides that are marked as congruent. Its base angles must be congruent as well. The base angles are the ones that are both attached to the base. The base is the side that's not congruent to the other two. Or you can also say that the angles across from the congruent sides, those are the base angles as well. Either way you slice it, x is 38 degrees because of the Base Angles Theorem. Okay, let's update our diagram and bring back the stuff on the interior of that triangle. How could I solve for y? Well, again, solving for y doesn't require any knowledge of triangles. If I just focus on this part of my diagram, I see a linear pair. And linear pairs have to add up to 180, so y must be 116 degrees because of the linear pair postulate. What about z? How could I solve for z? Now keep in mind that z is labeling that arc. So really I can ignore the 116 and the 64 and the line in the interior of the triangle and just focus again on the entire triangle. Since we discovered that that angle in the top left-hand corner of the diagram was 38 degrees as well, I have all three angle measurements and I can set them equal to 180 degrees. So 38 plus z equals 180, which means that z must be 104 degrees. And for my reasoning here, it's just the triangle sum theorem. We had already explained how we got to 38 earlier, so really all I did was add up those three angle measurements and set it equal to 180. In our next example, I see an equiangular triangle, and as we've discussed before, the angles of an equilateral or equiangular triangle are always equal to 60 degrees, because you could label them, you could call them W, in this case, W plus W plus W is equal to 180, so 3W equals 180, so W equals 60. We actually saw an example like that a few examples ago. So how could I use that information to help me solve for x? Well, yet again, it doesn't require any knowledge of triangles. If I just focus on this part of my diagram, I see that those three angles must add up to 180 degrees. 65 plus x plus 60 equals 180, so x must be 55 degrees. And that would be because of the linear pair postulate. Okay, how could I solve for angle y? Well, angle y is just in this triangle, the isosceles triangle on the left-hand side of the diagram, so that's what I'm going to focus on for right now. Since this triangle has two congruent sides, it must have two congruent angles, and those are the base angles. The base is the side that isn't congruent to the other two, so the base angles are the ones that are both attached to the base. You can also say that it's the angles that are across the triangle from the two congruent sides. Those must be the two congruent angles. So since I have 3 measurements now in this triangle, I can add them up to 180 degrees and find out that y must be 50 degrees. My reasoning again is the base angles theorem. That's what allowed me to put 65 degrees right here. And the triangle sum theorem, that's what allowed me to add them all up to 180 degrees. Okay, how am I going to solve for z? Well, for z, let's just focus on this isosceles triangle. Again, I have 2 congruent sides, which means I must have 2 congruent angles. The angles that are congruent are the base angles, the ones that are both attached to the side that isn't congruent to the other 2. Or you can say that it's the angles that are across the triangle from each of the congruent sides. Either way, you would come to the conclusion that the unlabeled angle in this triangle would have to be 55 degrees, because those are the 2 base angles in this triangle. So then I can add all 3 of those angle measurements together and set it equal to 180, and come to the conclusion that z must be 70 degrees. And my reasoning is the base angles theorem and the triangle sum theorem. I want you to pause the video and try this one on your own. It's pretty similar to some of the ones that we've seen so far, so let's see if you can figure out the values of x and y and z on your own. Let's see how you did. If I'm going to solve for x first, then I really just need to focus on this triangle in the diagram. It's an isosceles triangle, 2 of its sides are congruent, which means 2 of its angles are congruent. The missing angle would be labeled with x degrees because that matches the other base angle in this triangle. So I can say that x plus 94 is equal to 180. And that would mean that x must be equal to 43 degrees. And that's because of the base angles theorem. That's what allowed me to put x right here. And the triangle sum theorem, that's what allowed me to add it up to 180. Okay, now I'll update my diagram with 43 and 43. How am I going to solve for y? Well, y is one of the angle measurements in this equilateral triangle, and I know that equilateral triangles are also equiangular. So all 3 of the measurements here must be y degrees. So y plus y plus y equals 180, 3y equals 180, so y equals 60 because of the corollary to the base angles theorem. That's what allowed me to say that all 3 angles are y, and the triangle sum theorem. That's what allowed me to say that all 3 angles add up to 180. And then how am I going to solve for z? It's tempting to use something with the base angles theorem because z is one of the angles in an isosceles triangle, but actually you're just going to use the linear pair postulate. Those 3 angles must add up to 180 degrees, so z must be 77 degrees. There's one theorem that we haven't talked about yet, and that's what we're going to use to solve this problem. How am I going to figure out x, and how am I going to figure out y? Well, x and y are both exterior angles. They're on the outside of each of those triangles. And the exterior angles theorem tells us that you can add the 2 non-adjacent angles in the triangle together and set it equal to the exterior angle. So x has to be 158 degrees because of the exterior angles theorem. And likewise, I can say that y is 53 plus 90, so y must be 143 degrees, also because of the exterior angles theorem. In our next problem, we actually have 5 different variables to solve for. And on problems like this, it can feel overwhelming, and I know a lot of students just look at it, they're like, that looks hard, and then they shut down and they don't do anything at all. But some of the angle measurements here are actually really easy to solve for. So do yourself a favor on a problem like this and look for the easy things first, instead of just giving up. For example, v and 132 are linear pair. And we've been learning about linear pairs for months now. That should be easy. V plus 132 equals 180, so V equals 48 degrees. Easy peasy. What's another easy thing to solve for? Well, how about W? W has to be 90 degrees, right? It's next to another 90-degree angle. They form a linear pair, so if one side of it's 90, the other side has to be 90 as well. And really, that's just the definition of perpendicular lines. Since that's a right angle, those 2 lines have to be perpendicular. Perpendicular lines make right angles. W must be a right angle, which means it's 90 degrees. So see, you've already done 2 out of the 5 problems. What's next? Well, if I just focus on this part of my diagram, I see a right triangle. And the corollary to the triangle sum theorem tells me that the sum of the acute angles in a right triangle equals 90. So I can say that z plus 48 equals 90 degrees. You didn't have to use the corollary, you could just use the triangle sum theorem, and instead write that z plus 48 plus 90 equals 180. Either way, you'll get to the same answer of 42 degrees. If you did it my way, the way that's on the screen, then it would be the corollary to the triangle sum theorem. If you did z plus 48 plus 90 equals 180, then your reason would be just the triangle sum theorem. Okay, well, what about x? How could I solve for x? Well, I notice that x is attached to that angle marking, and I see a matching angle marking on the other side of my diagram. So really I could think about this whole thing being labeled as x degrees. So let's get rid of the y and the 42 and the 90 and that whole line. Actually, we don't need any of that. If these two angles both measure x degrees, and the third angle in that big triangle measures 48, then I can say that x plus 48 equals 180. So x must be 66 degrees because of the base angles theorem and the triangle sum theorem. Another way to have done that is actually using the exterior angles theorem. Since 132 is an exterior angle of this triangle, I can add the two non-adjacent interior angles, which are the x and x degrees, and set that equal to 132. So I get the same answer of x equals 66, but my reason would be because of the exterior angles theorem. On problems like this that are more advanced, that there's more parts to it, there's oftentimes going to be more than one correct explanation, depending on how you view the diagram. Well, we've still got one variable left to solve for. How am I going to figure out the measure of angle y? Well, it doesn't really require the use of triangles whatsoever. I'm just going to use the angle addition postulate. Since that entire angle measures 66 degrees, and it's made up of a y degree and 42 degree angle measures, I can add y and 42 and set it equal to 66, so y must be 24 degrees. And that's just the angle addition postulate. But of course, that's not the only way that you could have done it. You could instead focus on this right triangle right here, and say that since y and 66 are the acute angles of a right triangle, you can add them together and set it equal to 90, and you get the same answer of y equals 24, but this time your reason would be the corollary to the triangle sum theorem. The last thing I want to discuss today is how to classify a triangle by its angles and its sides just by looking at what the degree measures of its angles are. Here we have the angle measurements of a triangle, and I can add them together and set it equal to 180 degrees because of the triangle sum theorem. Combine like terms, subtract 6 and divide by 58, and I find out that x equals 3. But we're not done yet, because we weren't just asked to figure out what x is, we're asked to classify the triangle by its sides and by its angles. In other words, is it acute, is it right, is it scalene, is it isosceles, is it equilateral, what is it? So to figure that out, we're going to have to plug in 3. So 20 times 3 is 60, 13 times 3 plus 21 is also 60, and 25 times 3 minus 15 is also 60. So all three angles in this triangle ended up being the same measurement. That must mean it's equiangular. And if it's equiangular, then it must also be equilateral. So let's try that again. We're going to add the three angle measurements together and set it equal to 180 and get an answer for x. So then I'll take x and plug it in. 5 times 6 is 30, 10 times 6 is 60, and 15 times 6 is 90. This time I got three different angle measurements. And one of those angle measurements was 90 degrees. So that means that triangle DEF is a right triangle because one of its angles was 90. But what about its side lengths? It must be scalene. If you have three different angle measurements, then you must have three different side lengths. And that's what we call a scalene triangle. All right, I want you to pause the video and try this last one on your own. Okay, let's see how we did. I'm going to add those three measurements together, combine like terms, and solve, and I get that x equals 7. So I'll take 7 and plug it in. I get degree measures of 67, 46, and 67. All three of those angle measurements are less than 90 degrees, which means it must be an acute triangle. And two of the three angle measurements are the same. That means that two angles are congruent, and according to the base angles converse, if I have two congruent angles, then I must have two congruent sides. So my conclusions here would be that triangle GHI is isosceles because two of the angles are the same, and that means that two of the sides are the same. And triangle GHI is acute because all of its angle measurements are less than 90 degrees. And that's all you need to know about using the properties of equilateral and isosceles triangles to solve problems. In our next video, we're going to talk about what it means for two polygons to be congruent to each other, and how we can use their congruence to solve for missing side lengths and angle measures.